Hey folks, in this video we're going to be talking about my dude Hess's law. Let's talk about. So I want you, dear human, to be able to define Hess's law and use Hess's law and eat a light bulb without injury. So Hess's law is another method you can use for determining the delta H reaction, without actually carrying out that reaction. And this is useful for when you can't directly measure an enthalpy change in the laboratory for whatever reason. And if you also don't know the delta H of formation for products and reactants, because that's another strategy you can use if you can't directly measure a reaction. So what we can do is use the delta H of reaction for similar reactions to the ones we're studying, and use this to help us get the actual unknown delta H of reaction. So what we do is we modify these known equations so that we can add them together to give the unknown equation. And the things that we can do here are flip the products and reactants in these known equations, which will cause us to change the sign on our delta H of reaction. And we can also multiply or divide all the coefficients in a reaction, which will cause us to multiply or divide that delta H of reaction. This is kind of weird without an example, so let's look at an example. We want to determine the delta H of reaction for when we take carbon monoxide, CO, and burn it with oxygen to give us carbon dioxide. We can't do that directly for whatever reason. Totally could in actuality, but it makes a good practice problem. And so we know that we can take carbon and oxygen to make carbon monoxide, and we also know that we can take carbon and oxygen to make carbon dioxide. Well, using these two equations, we can add them together to get to this final equation. So one thing I want to do is make sure that all the reactants are on the reactant side and all the products are on the product side. And so right now I can clearly see I've got oxygen. That's cool. That's supposed to be a reactant. But carbon monoxide, that's not in the right place. So we're going to have to flip this equation around. But carbon dioxide, that's in the right place. So for starters, I think what I'm going to do is flip this around. But let's see what these guys add up to right now. Right now, that's not the equation I want. If I just add these two equations together, add up all the reactants and all the products, we can see that this is not what I want. So let's modify it. Let's flip that guy like I said we need to do. We needed carbon monoxide as a reactant. And you can see when I flip this around, I also changed the sign. It's now no longer a negative 221. It's now positive 221 kilojoules per mole. Well, that's great. Now this carbon monoxide is in the correct spot. That's flipping great. Oxygen is still in the correct spot. That's great. We just got to deal now with this carbon dioxide because there's not enough carbon dioxide in the picture. You know, if we add these two together right now, it's still not a pretty picture. The one thing we can do is cancel out things that are on both sides of the equation. So these oxygens actually get canceled out, and that's not great because now there's no oxygen left. And these carbons don't get completely canceled out. There's still going to be one carbon over here. So I think this should all get fixed if we double this equation. If we make it 2, 2, and 2. That'll give us the 2 carbon dioxide we need, and hopefully it'll take care of everything else. So when I double the coefficients in there, you will note that I also double the enthalpy of reaction. So now let's see what we have when we add these two equations together. I've got my 2 carbon monoxide plus 2 carbon plus 2 oxygen. On the other side, I have another 2 carbons. Well, those will get canceled out. And I have 1 oxygen over here. If I have 1 oxygen over here and 2 over there, one of those oxygens will get canceled out from both sides, which will leave me with whoosh, just the 1 oxygen. I wish that bar would go away. And I've got my 2 carbon dioxide on the product side. So this looks good. If you look at the things that aren't marked out with the red line, that's exactly what we want to have. And so now what we can do after adding these equations together is we can add together the enthalpy of reaction for both of them. So I'll just add those two numbers, bam, and get this negative 576 kilojoules per mole. Sweet stuff. Let's look at another example. Why don't you, based on what we did in that last problem, pause this guy and give it a shot. Make sure you're getting the reactants in the correct spot, the products in the correct spot, and making sure the coefficients on all of them look good. Cool, well you paused it. Let's go through this together. The first thing that I see in looking at this problem is that this guy, who I want as a product, is not in the right spot. So I'm definitely going to need to flip this equation around. What else looks weird? Well, hydrogen's in the right place. That's cool. And we've got carbon in the right place. That's cool. So these two guys might have to do a little something with their coefficients. But this dude, we're definitely going to need to flip. So yes, I see that. And I see that this thing is in the right place. So I'm going to need to, flip that puppy around. And remember, when I do that, I changed this from a negative 1299.5 to a positive 1299.5 when I swap my products and reactants. Well, that looks good, but I'm supposed to have 2 carbons here. So we should probably double that up so that I've got 2 carbons like I'm supposed to have in this reaction here. And the hydrogen situation seems good. I don't want to mess with this equation right now. And remember, when I put in these 2 carbons, I had to double my delta H of reaction. Okay, so let's see what this looks like when I add it all together. It looks like a lot, which is why I color-coded it. The stuff in black comes from the first equation, the stuff in blue comes from the second equation, and the stuff in pink comes from this last equation. So let's see if there's any things that are on both sides that we can cancel out. Immediately, I'm noticing that we've got carbon dioxide on both sides. So let's get rid of that thing. And we've also got water as a gas on both sides. If it's a product and a reactant, that means like nothing happened to it. So let's just cancel it out. What else we got? Well, now we've just got these oxygens, and you know what? I've got oxygen here and oxygen here. I should probably rewrite this so that A, I get rid of the stuff that I don't need, but also B, let's rewrite it to put all the oxygen together. And so now I can see, all right, I've got 5/2 of oxygen over here and 5/2 of oxygen over there. Is that correct? That seems right. Because I don't want any oxygen in this thing at the end. There's no oxygen in the actual equation, so when those cancel out, now I just have my 2 carbon plus my hydrogen gives me my C2H2. Sweet! And so now that I know that when I add all these equations together, it gives me the desired equation. I can add all the delta H's of reaction together to give me the desired delta H of reaction, which is a fabulous, what is that going to come out to? A positive 226.7 kilojoules per mole. Yeah, flipping, this guy really made it all positive. Anywho, that's the end of this video. I hope you understand the basics of Hess's law. I'm sure you could use a little bit more practice, but we can deal with that in person. Anyway, ta-ta. Have a great rest of your life.